Okay, I think we'll get started. So today's a fun lab. We are going to be interacting with a very important IC, the 74HC595 shift register, which normally operates as a serial in, parallel out shift register. And so what's happening there is data is loaded, the data are loaded 1 bit at a time, and once the shift register is full, I guess at any time, but once the shift register is full, you send an output enable, and then that gets outputted to 8 pins in parallel, and that output can then do whatever you want. There are a number of very good videos on the 74HC595 shift register on YouTube, so I encourage you to learn a lot more about this. It's a really important integrated circuit. We're going to stay focused on what we're doing in this activity with the PIC. So the pin out for the 74HC595 is like this. It's a 16-pin IC, and it's run with just 5 volts and ground. The Q pins are there's 8 of them. They are the data out, and so once the output enable, which is another pin, goes low, it's an active low, that's what the bar over means, it will send out to the outputs either 5 volts or 0 volts, depending on how the data was loaded in. That's loaded in via the data set pin, and in concert with the clock pins. There's a storage register clock and a shift register clock. We're going to be linking these two together and then just stepping them together. And so what happens is you send a signal, high or low, to the data set pin, and then on the clock rise, that gets written to the register. And then on the next clock rise, that gets shifted, and the next data, whatever the data is at that pin, gets written in. So if the data is changing and that's shifting each time, then you write in 1s and 0s, or highs and lows, into the shift register. And then again, as the output enable is brought low, then that gets sent out. There's a master reset pin, which we won't be talking about, and then there's this Q7 pin, which we also won't be talking about, but it's used to daisy chain together multiple 595s. And as we can see here, we've gone from the number of outputs, which is really just 3 for a PIC10F200, to 8. And so it's a way to expand the number of outputs or inputs if you use a different if you use a different shift register. But a way to shift registers are used to increase the number of input and output, and that's often what they do. Now let's connect now with the PIC. Here's the pinout diagram for the PIC10F200. The 5 volt rail and the ground rail here. GP3 is acting as an input. It can only act as an input, and we have a push button here. And once we push the button, that will initiate the sequence of events that will write a binary 8-bit number into the register through GP0. This will be clocked over by GP1, providing the clock pulses. And this was always confusing for me because just the nomenclature. I always think of a clock as a consistent set of pulses that just keep going. But that's not the case here. You only want to clock 8 times because we want to fill that register. And if we clock more than that, we'll just push those data off the register. And if you don't clock enough, then you won't fully fill the register. And then finally, the GP2 pin is acting to send this out, and that will be sent to an LED array. So there'll be 8 LEDs coming off of Q0 through Q7. There's a current limiting resistor here to make sure we're not driving too much current and frying the LED or frying the chip. All right, let's go to the circuit board and to the assembly program, and we'll see this in a little bit more detail. All right, so looking at the circuit board here, we can see the PIC10F200. This is connected to the PIC kit 5, which will help us program this. So these wires while they're important for programming the chip, they wouldn't be there if, in the field if you had programmed this chip and were running it. What we would need though is the two yellows here are showing the ground, and so this is to ground and this is to 5 volts to power the PIC. The output of the PIC is running to the data in for the 595, which we might not be able to see here under all these wires. That's coming from GP0, and then GP1 is serving as the clock. You might be able to see this. It's a little jumper wire, so that output is controlling both the storage clock and the shift clock, and we're just going to step those together. And then finally, the GP2 is going to be held high and then drop low to send the data out to the LED array, which we can see here. There are 7 wires here taking all but one of these back to this side of the shift register, Q1 through Q7, and then there's that lone Q0 that's sitting over on this side. That's carried by this white wire right here. So that's the circuit. Looks a little bit of a rat's nest here because we have to have all these LEDs and all these wires. But I think if you just systematically put it in and carefully connect the wires, you'll find you'll be able to get it wired up pretty quickly. So let's go to the program, and this is indeed a sample program to work with the 74HC595 shift register, which is a serial in, parallel out. The front part of this is always the same, and so this is where we set the configuration bits and bring in the include file for the PIC10F200. Gives all the opcodes and everything. And then over here we set the program counter, and that's sent to main. Now, like a lot of the programs that I've been doing, main, the first part of main here we're going to use to set the things that we only set once. And a big one is setting whether we're using the GP pins as inputs or outputs, and that's done with this binary literal. The last 4 digits are what's important here. And in this case, we want 3 outputs. Output is 0, input is 1. GP3 must be left as a 1 because that can only act as an input. But GP2 through GP0 can either be inputs or outputs. And so we want them as outputs here, so we set that to 0. Tris6, this writes, this binary is currently in the working register. This will write it to the Tris register. And then finally, we will have this next set of information here. The GP2 pin is by default the external clock pin. So we don't want that. We want to work with the internal clock, and we want to be able to use the GP2 pin as an input. And so the 0 here in this binary will do that, and then in conjunction with the option, that'll write this, which is in the working register, to the option register, which will change from the default to have GP2 as an IO. And most of the, I don't know if I'll even have any examples here where we're using an external clock pin, so it's good to set the GP2 pin as an input pin or an output pin. In this case, an output pin. This part here, this is probably just precautionary. This is going to set the GP2 pin as high. We know the output enable is active low, and so we want to hold this high so that we can load the information and then send it out all at once. Now we'll enter the main loop here. This 9 tells us how many clock cycles, but it's 9, the way I've got it decremented or set in the loop here, it's 9 minus 1 or 8. So this will fill, with 9 here, it will fill the register. That is stored in memory register 1-3 on the PIC, and then this is kind of the important part here. This is what we will write. So here, this is all ones, and that's the demo that we see on right now, and that will be stored in 1-4. Before we get into the nuts and bolts of this, let's look at this here now. So let's go ahead and change this to a 0, and we'll run this. And now this sets all but one. The least significant bit will be 0. So I'll press my button and on will come the lights, but this one is 0. So this one is representing the least significant bit side. So let's go ahead and change this. Let's call this a 1 and this is 0. And now we will turn off the most significant bit. So that one is off. And of course we could put another 0 in here, and maybe a 0 here. Oh, I got to make sure I don't have too many. Yep. And run this. And we have a representation. So the most significant bit is off, then there's 2 that are on, then an off, and an on and an off, and then an on. And so what we're writing here gets written to the LEDs over here. Let me put these all back to 1s. And we'll talk about this number of clock cycles here. So it's working again. Now let me change this to 8 and run this again. We can see we didn't get all of these transferred to the shift register. So we didn't have enough clock cycles there. And so I'm going to change this back to a 9 to make sure that we do that. Okay, so this is all set here. Now let's get into a little bit more of the nuts and bolts of how this works. Okay, so we initially set the clock pin to low, so we are not clocking in any data, and we're setting the data to low. So this is just sort of a resting state here, while GP3 polls. So this is just going to keep running in a loop until the button is pushed. So this will skip if set, and it's set when the button is pushed. So when it's set, it jumps across, and we will set GP2 to high. It should already be high, but we'll set it to high, and that way data won't be, the data are not coming out as they're being loaded in. They'll only come out at the end. Now we'll go into read bit by bit. And so what the strategy that's done here is that we put that binary number into register 14, and we're going to read the 0th bit and send that value to GP0. And so that's what happens here. We read the 0th bit. So what's happening is we clear GP0, so it's set to 0. Then we read this. If this is clear, then this was right to be clear, and we skip this. But if this is a 1, like it is when they're all 1s, for example, then we don't skip this, and we set GP to high, GP1 to high, so the GP0 to high. So this is a way to set GP0, so we'll default it to 0. Then if we read a 1, it will set it to high. If we read a 0, it will not. It'll leave it at 0. So that's how that's getting written in to. That's how the data is getting transferred to the GP0 pin. So those data are sent there one at a time, 1 bit at a time. Now what we do here is we want to have the data on a little bit before the clock turns on, because the shift register reads on the clock rise, and we don't want these both rising or both changing at very close time. So we've put in here just a several millisecond delay. And that's not important what the delay is, but this will set the data, then it will delay a little bit and run the clock. And that's GP1. So that will run the clock, and that will clock in that value. It will also then shift this to a spot in the next spot in the shift register, and then the next spot will be ready to read. Now, the strategy here now is we are going to rotate the data that are in the 0, 1, or the 1, 4 memory, the binary that we wrote in, and always be reading the 0th bit. So that's this rotate right function. So we slide the next bit over to the 0th spot and then roll the other one, rolls around. So what this does is it allows us to just put a window on that 0th bit and read that, shift, read, which is an effective way for doing this, because although we could read any individual bit we want, it's a little bit harder to implement that in this loop. This is a really nice way to use this. These two functions, rotate left and rotate right, are very important ones. And this is a good chance to use that here. All right, then it'll just go to read bit. I should say we decrement that 9 goes down to 8, goes down to 1, and so on. And then once we have read in all 8, we've actually decremented 9 down to 0. Then we're done. So we essentially have read everything in. Then we clear the GP2. So that going low, because it's an active low, the output enable is initiated and our values get sent to the array. So let's run that one more time here. This is all 1, so let's go ahead and run that. And we press the button. We should get all 1s. And just for good measure, let's go 1 0 1 0 1 0 1 0 and give that a try. Clock those in, and we get 1 0 1 0 1 0 1 0. And so this is a fun little project to work with the shift register. Again, the shift registers are really important integrated circuits that you should familiar yourself with, and like I mentioned earlier, there's a lot of great resources out on YouTube to learn about these things and learn how they're used in different circuits. So I think that would be very beneficial for you. And so that essentially covers what we're going to be doing with the 74HC595. We will be working with a parallel in serial out register, in which case we will set with some dip switches the highs and lows, and that will be read into the PIC. So the opposite of this one. And between those two, then you've seen some good examples then of the way the shift registers are used and how they can be used in conjunction with the PIC10F200. And the big picture here is that it enables us to expand the capabilities of the PIC10F200 by increasing the number of inputs and outputs. All right, with that, I think we'll close this lab.